Okay guys, so we're going to do a combination circuit example. We're going to start out, this one has a 12 volt battery and it runs and splits into a 2 ohm resistor, and then on this side it has a 5 ohm and a 6 ohm resistor. And then it comes across this way, and there is a 10 ohm resistor at this point. Okay, so we need to see first of all that this is not a series circuit and it's not a parallel circuit, it's a combination of the two. If you look, there are 4 resistors in the circuit. There's certainly more than one path, so it's not a series. And there are not 4 independent loops, so it's not a full parallel circuit either. Okay, so the first thing I always look at when I'm looking at a combination circuit is, are there any resistors where if I took them out of the circuit would go completely dead? And the answer in this case is yes. This circuit, the 10 ohm resistor, is the one where if you took it out, the circuit would go dead. So that means it gets all the current, gets the total amount of current. That's important. The other ones are not going to get the full current. They're going to get some fraction of the current because it splits up. Okay, so our first job, our first order of business is to find the equivalent resistance of the circuit. And we want to work from inside out. So I see over on the right that the 5 and the 6 ohm resistor, for example, if we imagine boxing those like this, they are connected in series. There's one wire between them. So that means that their total resistance, their equivalent resistance, is 11 ohms. So I'm going to do that. And then I notice that that 11 ohm box is in parallel with the 2 ohm that's next to it. You can see that the wire at the top here and the wire at the bottom here connect the dotted line box to the 2 ohm resistor. So they're in parallel with each other. So to find the equivalent resistance of that setup, I'm going to do 1 over 2 plus 1 over 11 equals 1 over the equivalent resistance of those. Okay, so we could do a common denominator here of 11 over 22 plus 2 over 22 equals 1 over our equivalent. So this gives us 13 over 22. And of course you can use your calculator for this as well. So 22 over 22 over 13, excuse me, is our equivalent resistance. So our equivalent resistance of those is 1.69 ohms. So you want to imagine that everything now I'm going to make a circle. Everything inside my circle has a resistance of 1.69 ohms. Okay. All right. Now, the current flows out of the battery, goes into the circle, comes out of the circle at this point right here, and then goes to the 10. So the 10 is in series with the 1.69. The total resistance of the entire circuit is 10 plus 1.69, which is 11.69 ohms. I can then find the total current by doing the battery voltage, which is 12 volts, divided by the total resistance of the circuit, 11.69 ohms. So we're going to get just over 1 here. 12 divided by 11.69 gives us 1.03 amps. Okay, now I'm ready to set up my RIVP chart. So I can put my resistances in. I have a 2 ohm in the original circuit, a 5 ohm in the original circuit, a 6 ohm, and a 10 ohm. Now, when we first started talking about this circuit, we realized that the 10 ohm resistor gets all the current. So I'm going to put that current, 1.03 amps, here. And now that I have R and I can find V. So 10 times 1.03 is 10.3 volts. And to get the power, I could do 10.3 times 1.03. And we'll go with 10.6 watts. So that's all set. Now, the next thing I'm going to do is I'm going to use the loop rule. I'm going to start at the battery, so start here. We go up by 12 volts as we approach the battery. Then we're going to go left, so we're going to go this path right here. We hit this 2 ohm resistor, we're going to drop some voltage, and then we're going to hit the 10 ohm resistor and drop 10.3 volts, and we're back at the battery. We have to drop a total of 12 volts, according to the loop rule. So if I dropped 10.3 at the 10 ohm resistor and an unknown amount at the 2 ohm resistor, and they have to add up to 12, then the voltage across the 2 ohm resistor is 12 minus 10.3, which is 1.7 volts. So that's going to go in here. Once I have the voltage, I can divide to find the current. So 1.7 divided by 2 gives me 0.85 amps. And I can get the power by multiplying I times V. 0.85 times 1.7 is 1.45 watts. Okay, now, for the remaining part, I'm going to use the junction rule. I'm going to pick this point at the top of the split, right here, as my junction. I know that coming into that junction is the total current because there's only this single wire at the top carrying all the current in the beginning. And that current is 1.03 amps. So that's what's going in. We figured out that the current flowing through the 2 ohm resistor is 0.85 amps. So the amount of current that's flowing through the right part over here, going into the 5 and the 6, has to be whatever's remaining. So 1.03 minus 0.85 is going to give me 0.18 amps. So that means this gets 0.18 amps, and so does the 6, because they're in series. They get the same current. We can now multiply to get voltage. So 5 times 0.18 gives us 0.9 volts. And 6 times 0.18 is 1.08 volts. We can multiply again to get power. 0.9 times 0.18 is 0.162. And 0.18 times 1.08 gives us 0.194 watts. So you'll notice that the 5 and the 6 get the same current, which makes sense because they're in a series with each other. And you'll also notice that if you go around a loop in the circuit, you're going to drop a total of 12 volts, whether you take the left path through the 2 ohm resistor or you take the right path through the 5 and the 6 ohm resistor.